Yeah, first let me start with thanking the organizers for inviting me to this beautiful place and giving some lectures here. So today I'm trying to give you some kind of an idea how, as a chemist, we think about topological materials and what kind of chemistry tricks or intuitions we can use to identify and find new ones. And so my first lecture will mostly be focused on chemical principles and how this can be used to find the next generation, basically, of topological materials. And then in my second lecture, I will discuss a little bit more about crystal growth and RPS measurements, so that you get an idea of what, like, once you have an idea, what you actually have to do to realize that. But let me start a little bit with some motivation, like why we should do this. So first of all, this is really some work on the interface between two disciplines, because we make materials which are of interest for physics or physicists, and we use chemistry knowledge to make them. And this is like not a really densely populated interface from sciences so far. So there's so many chemists who make material or compounds or things which are of interest for biology. So they're working on drugs or anything. And so there's a lot of communications between the fields. But it's really thin in the chemistry physics world. And I hope that this lecture and this talks can motivate you to strengthen this a little bit and advance this. And this is just a really short motivation of why we should think about making new materials. I mean, of course, for one, it's just that you want to find all these exciting new effects that are being predicted by condensed matter theorists. But it's also, I really enjoyed reading this article which appeared in Science News last December, which was about the process of developing quantum computers at some point, and it listed all different qubits which are out there, and said listed the advantages and disadvantages of them and how they can maybe use to assemble one day a quantum computer. And then they list topological qubits, and they say pros, greatly reduces all the errors, cons, existence not yet confirmed. Okay, why is this? Because we're still lacking a good material which can do that, right? So we still need more materials and better ones to ever fulfill this goal. Okay, so how can we do that? How can we find materials? And so what I try as a chemist is that I try to understand this triangle, how are those things connected? How can I connect the crystal structure and chemistry, so how the atoms are really arranged and put together, with the electronic structure and the properties. And so if you understand all three edges of this triangle and how they're connected, you have some predictive power of really predicting a material with a certain property. And so today I want to mainly focus on this part, understanding crystal structure and chemistry, because this is the part I feel where chemists can teach the most in the lecture about this process. Okay, so the structure of matter. So what does this mean? What can we learn about how atoms are arranged, about some properties? Okay, this is basically what the field of solid-state chemistry has been doing for a long, long time, trying to understand how matter is composed to, what is the structure of different matters. And so really, traditional solid-state chemistry might appear rather boring, because all it cares about is really figuring out how atoms are arranged and how a crystal is formed, and there wasn't so much caring about the properties. However, this knowledge that was gained is really important for us now to then link it to properties. And so traditionally, solid-state chemists were just thinking about, okay, how are the atoms bonded with each other, what is the structure, what are stable compositions, and what compositions or what elements can I put together and I don't form anything, and how can I relate this to some rules, like counting valence electrons or thinking of the sizes of atoms. And so this is a typical figure for a solid-state chemistry paper, where you have a structural map, basically, where you map some elements on each column, and they say, okay, you have different regions where different phases are formed, or some regions where a phase is not formed, and so therefore you have some understanding about what is possible to have. And I want to start just in general with showing you those different structures, because it might not be intuitively to be understand that if you have, for example, 3 elements, and you have them in a composition of 1 to 1 to 1, that they can form completely different structures. So you can see those are just the 5 most common ones. There are many more available just for one-to-one-to-one composition of elements, ternary compound. And so depending on which arrangement the atoms have, you have completely different properties. Some of the compounds I draw here are semiconductors or insulators, others are metals. And so it is what structure they're adopting is largely governed by those 3 things. The electron counts, how many valence electrons do the elements have, the sizes of the elements, so some like ratios of you have a small and a large one together, are they all large, are they all small, and then the type of bonding between them. So the bonding can be more covalent or more metallic, or the bonding can be really ionic, and that also creates some difference in the structure. And so electron counting is the first really nice rule you can use to find if a structure is stable or if a certain type is formed. And this works especially well for ionic compounds. Because if a compound is very ionic, you need to have a charged balanced compound. So the electrons need to be balanced to have a salt-like structure. And for this, you need to have either 8 or 18 valence electrons, so completely filled shells, to have a stable compound. And so this is also a useful technique to think if you have a semiconductor or not. So if you want to look for topological insulators, you don't even need to look at things which are not charged balanced. And so you do the process is relatively simple. You look at this periodic table and you have a number for each column, how many electrons to count. You add them up, you see if they're 8 or 18, and you see if you have a charged balanced compound. And it's just a little bit more complicated if you have a formula somewhere you have 2 of those more electronegative ions, like N ions, then you have to divide by this number to again see if you're charged balanced. And so this works really well. So this is a slide I stole from Claudia. I hope she's not going to tell you the same thing later. But if you have a semiconducting compound, so you all might know gallium arsenide, you have 3 and 8 electrons, it's 8, so you have a semiconductor. But you can extend that to more complicated materials, and for example, put here one with 1 and 2 electrons, and again have 8, and you're still going to have a semiconductor. Or if you add d electrons to this, you count to 18, and if you have scandium, platinum, antimony, where you wouldn't intuitively think it's a semiconductor, still, because they count match, you have a semiconducting compound. And so you can see that here in this band structure plot that, for example, you know all cadmium telluride and mercury telluride both have 8 electrons per valence cell, and they're charged balanced compounds. So here you have the gap, here the band's touched, but it's still a charged balanced compound. There's a 0 band gap here. And the same works for more complicated compounds like scandium, platinum, antimony, or scandium, platinum, bismuth, where you wouldn't intuitively think. Okay. And so while electron counting to 8 or 18 really often works well, and it doesn't always do the complete trick, sadly. Otherwise, the chemistry would be way too easy if you just would need to know how to count to 8. So this is a story about a phase a friend of mine during my PhD was working on. And so she said she found a new stable phase, lanthanum, gold, antimony, with a composition of 1-to-1-to-1. And mentioned it to me because I was working a lot on 1-to-1-to-1 phases. And at first I told her, I don't believe you, because I counted the electrons, and it has 19 electrons. And those 1-to-1-to-1 phases usually want to have 18 electrons. So I told her, I don't think it's correct. You must have some deficiency or something. But then we realized when we solved the crystal structure that actually the gold atoms here have a really close distance to each other. So they're sharing electrons, they're forming a bond, and then those 2 electrons in the bonds are localized away from the valence electrons. They kind of move further away from the Fermi level, not to the core, but you could basically treat it like this. And therefore, you subtract 1 electron per phase, and you're back to a pseudo 18 electron count. And so actually, if you calculate the density of states, so of lanthanum gold tin, which would be the one with 18 electrons, and compare it to the one of lanthanum gold antimony, you see both of them, the Fermi level falls in a pseudo gap, so both of them are like charged balanced compound. Okay, so this tells us that there can be bonds in crystal structures and we still have something charge balanced. And this can be important if you want to look for semi-metals or semiconductors, which might be topological, because we cannot just rule out everything where the electron counts seem to not fit. And actually, this is part of a large rule or large phenomenon which has been known in solid-state chemistry for a while, which is the Zintel concept. So Zintel phases are phases which are semiconducting, but they don't appear so if you just look at the electron count. So a very famous example is this calcium silicide here, which is a semiconductor, but if you would count the electrons, you would count 10, and even if you divide it by, because there's calcium Si2 by 2, you would count 5 electrons per silicon. This is nothing charge balanced, right? You think it has a half-filled p-band. However, when you look at the structure, you can see that each silicon is bonded to 3 other silicons. So each silicon is sharing electrons with the other ones, and then the electron count matches again. Okay, and we have a charged balanced compound. And so I just showed you 2 different examples. So one time we had more electrons than we expected. We had 19 instead of 18. The other time we had less than we expected. We had 5 instead of 8. And so those are the 2 common kind of bonding things you could have in crystal structures, polycations and polyanions. So in the one case, the electrons share. So in this case, the electrons the elements share electrons to have the complete charge balanced compound, and in the other ones, they use the electrons in the bonds to localize to go away. And so if you know the crystal structure, there's a very easy thing to check if you still have a charge balanced compound. So you just, we already did it intuitively, but you can just follow this formula, which here is a bonding order. And so you just subtract the valence electron count you get. So here we had 5 per silicon from 8 or 18. And then you get the bonding order. So this is the number of bonds you would expect to appear in the crystal structure. And you match it with the structure and see if you actually find this number of bonds there. So in the case of calcium silicide, you would subtract, you have 8 minus the 5 valence electron count we have, and you would get a number of 3, a bonding order of 3, and then you see it has 3 bonds, and then you know, okay, great, we have a charge balanced interface. However, this doesn't match, and we would get 4 here, then you would have a metallic compound, okay? So why am I telling you this? So here's a Dirac line node material you might have heard about. This is zirconium silicon sulfide, and if you look at this material, you will see that it's only charge balanced if you consider the Zintel concept rule. So if you count the electrons, you count 14 per silicon. And so if you subtract this 14 from 18, you get a bonding order of 4. And you can see that here, those are the silicons. Each silicon is bonded to 4 other silicons. So therefore, this is a charge balanced compound, although it would appear metallic. Okay. Okay, so this was electron counting, but then there's another thing we need to be careful about, and I think often it is disregarded in the prediction of new materials, and it's just why I really care about this. This is that size really matters. So the size of the atoms is important. So this is this typical structural map you can have in solid-state chemistry, where you plot the radii, so the size of the atoms in your crystal structure on one axis, and also size of other atoms on the other axis. So this is a map for X, Y, Z phases, so 1 to 1 to 1 phases again. All of them have 18 electrons, so all of them are charge balanced. And we put the radii of the X atom here. So the X atom is barium, strontium, calcium, or magnesium, some kind of rare earth. And then we put the size of the other 2 here, like the sum of the sizes. And then you see that there are clear regions where the structures are different. Okay, so it really matters. So the ratio of the radius really matters. They can have completely different structures. And then also some of those structures are semiconductors with large gaps, and others are semi-metals with really overlapping density of states, pockets, and everything. And this is dependent on the structure. So it's not only electron counting, it's also size that matters. And for example, for oxides, there are some really nice rules you can follow to have an idea what the sizes do, because in oxides chemistry, or even very other really ionic compounds, you can take the ratio of your cation and your anion, which would be oxygen, and depending on the ratio, you can get the coordination number, which is possible. So if you have a large ratio, you will have a cubic coordination of your cations. With an intermediate one, you can have an octahedral coordination. And with really small ratios, you can have a tetrahedral coordination. And so if you want to make up a new compound based on this, you have to make sure that it fits those rules. Okay, and we'll come back to this later of how it doesn't work in some cases. Okay, and then lastly, I said the type of bonding is important, and I already mentioned it a little bit before. So we care a lot about electronegativity difference of elements. So this case like this in the periodic table. Here's very electropositive, here's really electronegative. And if you have elements which are far away from each other in the periodic table, you will have an ionic compound, and then charge balance is extremely important to actually have a stable compound. And if you have elements that are closer together to each other, you can have metallic compounds, and charge balance is not that important. Okay, so this was a brief overview about traditional solid-state chemistry and the rules you can have. But then in a little bit more modern times, solid-state chemists started to try to link structural motifs, like as a common structural feature, to some properties. And so this has been famously done with iron-based superconductors, which all share this structural same motif, and they all are superconducting. So there you can kind of link, okay, if you have this structural arrangement of iron arsenic tetrahedra in a compound, you can expect it to be superconducting. And so you can also do this with different types of properties, and you can try to find other structural relations and link it to a property. And so also an idea is this can we do this with topological materials or direct semimetals? Can we find a structural motif and link it to having this property? Then at the beginning of my triangle, I said that we also want to link somehow structure to electronic structure and to properties. And so this is how chemists learn about electronic structure. I know you look at this much more complicated, and I will come back to normal electronic structures, but this is what we learn, yeah? And basically we just differentiate between metals, semiconductors, and insulators. But the nice thing is if you just know how to count electrons, you can already differentiate without even knowing the crystal structures between those three basic types, right? Because it's charge balanced, it's going to be either that or that. And if it's not charge balanced, it's going to be a metal. And then also, if you look at the electronegativity difference, or like if the elements are very heavy or not, we can get an estimate about if it's going to be a semiconductor or an insulator, because we will intuitively know that sodium chloride, which is a very large electronegativity difference, will be a wide bandgap insulator, whereas gallium arsenide, where the electronegativity difference isn't as large, will be a semiconductor. So and then you can also try, if you understand a little bit about band structures, not all chemists do, but if you learn that, then you can try to do the same trick we do with crystal structures and try to find common motifs in an electronic structure and link this to a property. So this has been done with searching for this Van Hove singularities to find a superconductor. But now with the discovery of topological materials and the opening of this field, or Dirac materials, it becomes really easy to use an electronic structure and somehow link it to topological properties of a material. Okay, so this is the timeline of the discovery of topological materials, and most of those, or I think nearly all of those predictions, the theory was there first. So the question is, can we also predict a material and not just make something where theory has come up for, but predict the material ourselves and then realize it? And so here's the full timeline, the starting of the basic TIs, but in this talk I will focus on this later, more modern part of the topological materials discovery. So let's just start with Dirac semimetals. So I don't really need to tell you what Dirac semimetals are, I'm sure. So they're 3D analogs of graphene, have the same electronic structure of graphene, but in 3 dimension. And we care about them because they have the same exceptional properties as graphene. I just want to tell you how I think about the electronic structure, because this will help you to understand my thought process of finding new materials. So if you look at the normal band structure of an insulator where you have a band gap, and then just think about decreasing the band gap with maybe putting heavier elements in it or decreasing the electronegativity difference. You can have this kind of band structure with a band inversion or a negative band gap. And then you have those two crossing points where the bands cross. And the question is this crossing allowed or forbidden? And so this depends, if it's allowed or forbidden, it depends on the irreducible representation of the band. So it depends on group theory, so on symmetry, but also on orbital character of the bands. Okay? So the orbital character is a little bit sketchy. That doesn't really help us, but the symmetry can help us a lot. And so if you want to have a crossing left in your band structure and have a 3D Dirac semimetal and don't want to have it completely gapped, you need to have two different IRAPs crossing. And for this, it needs to be possible by symmetry reason that two bands have two different IRAPs. And so if you even include spin-orbit coupling, so if you look for double groups, then this reduces the amount of symmetry groups where this is allowed to only the ones which have C3, C4, C6 symmetry. Okay, so for me as a chemist, this means I can skip everything monoclinic, everything orthorhombic, everything triclinic, because this doesn't have the symmetry element. And I can focus my search on cubic, tetragonal, or hexagonal materials. Okay, so this is the first guideline rule is, okay, we need high symmetry, okay? Okay, here's again, I mean, I don't know, I think this is easy for you, but here's again how you see how spin-orbit coupling reduces the amount of IRAPs, why we have, for example, in the C2V point group 4 possible ones without it, they're reduced to 1 with spin-orbit coupling, but with the fourfold axis, we still have 2. Here's important to point out, because this also depends on orbital character, if we have a fourfold symmetry axis, it's possible to have a 3D Dirac semimetal with two different IRAPs, but it's not a given. Okay, so this is just some guideline. Okay, so we want to have high symmetry materials. Then this is a charged balanced band structure. We started this process here from a charged balanced compound. So we want to have the correct electron counts. We want to look for a charged balanced material. And then we want to have a zero density of states here. We just want to have the Dirac crossing there. So we need to have somehow a good ratio between electronegativity difference and spin-orbit coupling so that we don't have a two metallic compound, but we also don't have a wide band gap insulator where we would never have a band inversion. Okay, so we have three rules: high symmetry, electronegativity difference, spin-orbit coupling, and charge balance. Okay, so let us look how this works for the known 3D Dirac semimetals. So this is cadmium arsenite, the first one discovered. And here you can see that here it's this brilliant zone, and you see that we have the C4 rotation along gamma Z, and this is where the protracted crossing is, and along gamma X, this crossing gets. Also, if you count the electrons here, we have 8 per arsenite, so this is a charged balanced compound. And so then, if you think about electronegativity difference, okay, that's not that high. Those compounds are relatively close together in the periodic table, but they're also not too heavy. Okay, this is still kind of a hand-wavy argument. I will get back to this later. So here we have sodium-free bismuth. This is another really famously known 3D Dirac semimetal, and again, we have the crossing along the gamma A line, so where this C6 symmetry line is. This is hexagonal and not somewhere else. We have a charged balanced material. And we have a much higher electronegativity difference than in cadmium arsenite, but therefore also much more spin-orbit coupling. So it works again. Okay, still some kind of hand-wavy, this argument. So that's why at some point, Quinn Gibson, who was also a grad student at Princeton with me, and we wanted to somehow get a better feeling for it and try to quantify this spin-orbit coupling versus electronegativity difference enigma to get an idea when this is actually good for having a clean 3D Dirac semimetal. And so for this, we started to look at this barium, silver, bismuth family of compounds. So the barium, silver, bismuth is shown here. It has 18 electrons, and you can substitute the elements isoelectronically, and you stay in the same structure type. So those have hexagonal structures, and they can have band crossings along the gamma A line where the 6/3 symmetry is. But you see here, for example, already that barium, silver, bismuth is very nice and clean 3D Dirac semimetal. But strontium, silver, bismuth already has the crossing up here and some mixing through it. So basically, this brings us back to the structural map we had here before. So all those orange phases are the phase where the 3D Dirac semimetal is possible to have, and those are all the compounds. And so we tune what? We tune the electronegativity difference in the phase along this arrow here. So we have some degree of tunability. And so then we made some plots. So we calculated all those different band structures. We looked if there's a direct crossing or if it's not there. And we looked how much other bands are crossing them. We quantified it by the amount of density of states at the Fermi level. So if there's a lot of other things interfering. If there's not a lot, it's relatively clean. And so, so the density of states at the Fermi level is plotted on the y-axis here. And then we made two different plots versus the x-axis. On one plot here, we plot the total nuclear charge, which is somehow a measure for the amount of spin-orbit coupling because it increases with z, and divided by the electronegativity difference of the elements. And then here in this plot you see, so the red points, they don't even have a direct crossing, and the orange points, the direct crossing is there. And so there's a clear phase transition basically of when you can have that and when you don't have a free direct semimetal. So is there a band inversion or not based on spin-orbit coupling and electronegativity difference. However, we have a clearer trend if you just look at the nuclear charge on when there are fewer density of states at the Fermi level. So this means that the spin-orbit coupling or the heaviness of a material is important to reduce the number of states that are interfering with it. So we can find some trends here. Okay, so those are some rules for finding 3D Dirac semimetals. So we want to look for, as I said, charged, balanced, highly symmetric materials. And then the question is, can we also find similar rules for wire semimetals? Okay, so wire semimetals is a problem that now instead of a fourfold degeneracy, you have a twofold degeneracy, and you get that usually by breaking either inversion symmetry or time reversal symmetry in your fourfold degenerate system. And the problem is if you have an inversion asymmetric system, you often have those crossing away from high symmetry lines, so we cannot really use the concept we use for 3D Dirac semimetals anymore. So looking for wire semimetal in inversion asymmetric compounds is really messy, and chemistry doesn't really help us, sadly. However, time reversal symmetry, we can do something about it, and I will come back to this in my second lecture, because as chemists we know those types of elements that are likely to order magnetically, and we can try to look for compounds with that, where the symmetry rules for Dirac semimetals apply. Okay. Then lastly, nodal line semimetals. So this was the most recent thing on the timeline, and so what can we do to find this? So if you look at this diagram again, nodal line semimetals are those here where we have the band inversion and it doesn't gap everywhere. So this is really hard because we need really, really high symmetry Brillouin zone if you want to consider spin-orbit coupling. So we need to have the nodal line somewhere along a C6 rotation axis, which is usually not possible in a crystal structure. So therefore, it makes much more sense from a chemistry perspective if you want to look for nodal line semimetals to look for materials with very light elements and highly symmetric. Okay? And I will also come back in my second lecture how this can work in reality. Okay, so now we went briefly through the last end of the timeline and how chemistry can help us to find such materials, but the question is what is next? What is the next big thing? And I think you have lots of suggestions about this here, and probably in the schools already lots of ideas were given. But the one I want to focus on, because I like it, is actually a really nice chemistry problem, is Dirac materials or other materials which have some non-symmorphic symmetry options. And just want to give you a brief introduction what that means. So, I mean, I don't know how many people of here are familiar with this, but non-symmorphic symmetry is a symmetry elements where you have some kind of translational symmetry with it. So that means you can think of it like this footsteps, where you have a glide plane, where you have a mirror and a translation, or the spiral staircase, where you have a translation and a rotation. And so what happens to your lattice if you have a non-symmorphic symmetry element is that it expands. So here you have a symmetry. Here you have a symmorphic lattice, and you have one atom per unit cell. And then here's drawn a non-symmorphic lattice where there's a glide mirror, so it's only in 2 dimensions here. And you see the unit cell is larger, so now we have 2 atoms per unit cell, okay? And so we expand real space, and if we expand real space, we fold K-space. And if you fold K-space, what we do to our band structure is that this band becomes folded, and then here we find a point where the bands have to stick together, so they're forced to be degenerate there because of this expansion in real space and folding in k-space. Okay, and so this can result in Dirac semimetals because this can be a 4-fold crossing. And this was actually the very first concept in 2012 to predict a 3D Dirac semimetal. So before cadmium arsenite was discovered or predicted. Okay, this was the very first idea how you could realize a graphene in 3 dimension. And then it was expanded by some people who are also in the audience here, that you cannot have only 4-fold, but also higher or different fold degeneracies like 3 or 6 or 8 folds because of those non-isomorphic symmetries. And that could even be a potential to find new types of quasi-particles, so maybe this might be the next thing on the timeline if it's realized in this different manifolds of compounds. Okay, but here's the problem. So if we now would look at any non-isomorphic material, so those degeneracies have to be there because of the symmetry element. But if now any of those materials would be a 3D Dirac semimetal or a new fermion material, then our job would be done. It would be super easy. We just make one. Most of the materials are non-isomorphic, so there wouldn't be much to do. But the problem is that when we looked at the conventional 3D Dirac semimetals here, like cadmium arsenite or sodium bismuth, those were charged balance materials. And they're charge balance and the Fermi level is still here where we want it to be. But non-isomorphic materials are different because we folded the band structure. Now, if we do the chemistry rule of charge balance, where we don't count per unit cell, we count per formula unit. And then, when the chemist says charge balance, the Fermi level is always up here, where it's trivial and nobody cares about it. So if we want to move the Fermi level to the point we care about, we need to have a half-filled band, so 1 electron per band. And this is chemically extremely unstable. And actually, even worse, if you want it to be isolated, so if you don't want any other pockets to cross, then there are lots of different mechanism compounds like to do to avoid this kind of isolated half-band. And so you might be familiar with some of them. So what happens to compounds where there's an isolated half-filled band is that they like to undergo piles, distortions, or charge density waves, where they distort the lattice to actually reduce this kind of crossing and gap out, or they like to be Mott insulators, which does the same thing, same trick, so the crossing we care about gets gapped and it's not there anymore. Okay. So we need to find a trick to come around that. And I just want to go, so there's one prediction, the very first prediction of the 3D Dirac semimetal has the problem with a half-filled band, and I just want to give you an idea with the chemistry rules I told you before, why it can be so critical to predict, to just like hand wavy predict a material with a half-filled band. So first of all, I want to point out, I really like this paper. This is a really great paper. It was the first idea to use non-isomorphic symmetry to create those 3D Dirac semimetals, and it's a great theory job. The problem is that one material suggested here, bismuth O2, will sadly never be realized. And I hope I can make you understand why. So the idea was, okay, we have silicon dioxide, which is a non-isomorphic crystal. So you see the crystal structure here. And this is quartz glass. And it has, like you expect, this degeneracy at the X point. Okay, but it is, if you look at the energy scale, at minus 4.5 eV. And this makes sense because quartz, you might know it from glasses or anything you have. It's a transparent insulator. It has a huge band gap. So the feature we care about is down here, 4.5 eV below the Fermi level. And then, so the idea in the paper was, okay, if you put bismuth here instead of silicon, we add an electron bismuth with one to the right of silicon, and therefore we shift the Fermi level to the place we want it, and now we have the crossing exactly at the Fermi level. And also they use bismuth, which is much heavier than silicon, to lift this close to degeneracy, those two bands here, a little bit further away, so this is a more clean Dirac cone. Okay, why does this not work? So one is, I mentioned in the beginning that the ionic radii are important to form a crystal structure. And so if you look at the rules again, so I listed them again here, you take the ratio of the metals, so in our case silicon versus oxygen or bismuth versus oxygen, and you get the coordination. And so you can look up the radii, and under this link I put here, this is the Shannon Crystallographic radii, they're all listed in the internet, and you can just go to this page and look at radii of materials. So the radius of oxygen is 1.4. If you look up the radius of silicon So it is 4 plus in this compound because silicon O2, oxygen is 2 minus, so 2 of them silicon 4 plus. If you look up the radio of silicon with charge 4, and then tetrahedral coordination, because you see here there is a silicon and there are 4 oxygens around it in the structure they draw, then we find an ionic radius of 0.2. If you divide 0.2 by 1.4, we get something much smaller than 0.4, and so that fits into the tetrahedral coordination. Okay, so silicon can fit in an oxygen tetrahedra, no problem. So now let's do the same thing for bismuth. First of all, if you look at online and you look for bismuth 4 plus, you don't find it here in this table, and I will explain to you in a moment why. But okay, let's just look for any bismuth. Coordination 4 is also not given here, so this already should make you suspicious. But okay, let's take the smallest ionic radius ever measured for bismuth, which is 0.76, just to have an idea. And if you divide 0.76 by 1.4, you get 0.53, and this is larger than 0.41. So there is no way bismuth will ever fit in an oxygen tetrahedra. It just doesn't fit from the size, okay? You can only have it in octahedron or anything else. So you can't just replace that here. Yeah? Difficult. I mean, the problem is then you still would have to make the bismuth smaller. I mean, maybe under very high pressure you can change the coordinations, but so far there's no known phase. So it would be listed here if bismuth would ever be observed in a tetrahedra. So I think you need to apply a lot of pressure. Like, pressure does give you a little bit of leverage, but this is a lot larger, and it's also for bismuth 5 plus, so if it's smaller than 4 plus. So pressure pushes you a little bit about boundaries of the phase diagram, but doesn't give you a huge. Maybe if you get to apply like pressures like in the core of Jupiter or something, but yeah. Okay, and then the second problem was bismuth 4 plus didn't appear on the list, and that's because it doesn't exist. And so why does it not exist? So there's some effect in chemistry, we call it the inert pair effect. You might know it as relativistic effects in the more physics world, which is that if you have an element, your nucleus has a positive charge and the electrons have a negative charge. And so the reason atoms are still extended and have such a large electron count is that they shield each other from the positive charge of the nucleus and they don't get sucked too close to it. And so then if you have electrons in an S shell, they shield each other really well from the nucleus charge. But if you have it in a P or D or other shells, they don't really do the job as well anymore. And so if you come here and you start adding F electrons in a lanthanide, the shielding gets worse and worse and worse, and this is why the atoms contract actually along this lanthanide row. So they get smaller and smaller and smaller. And also then, for example, if you go at this part of the periodic table between zirconium and hafnium, you basically have the same size, although you add a complete new shell. And the reason in this contraction is that the electrons feel the nuclear charge more predominantly, and then if you come to this part of the periodic table where bismuth is, the 6s electrons, like the next fierce one, this feels the nucleus charge very heavily and gets lowered in energy. So why you would think this is the orbital diagram of bismuth with 6s electrons, actually the 6s electron gets lowered in energy and it's down there because of this nuclear charge. And so therefore, those 3 electrons of bismuth are easy to oxidize, and those 2 are not. So bismuth likes to be 3 plus. Okay, then if you have a 4 plus bismuth formally, it often separates into 3 plus and 5 plus because it doesn't like to have just 1 electron in there. And so there's no known example of a bismuth 4 plus compound. So if you actually could make bismuth O2 with bismuth 4 plus and bismuth in the oxygen tetrahedra, much more than having a new free-to-drug semi-metal, you might get a really fancy prize in chemistry for establishing those rules. Okay. And so here's another example about this bismuth 4 plus. So there's a very famous compound, it's barium bismuth oxide, which maybe some of you know who work on superconductivity, because if you dope that with some hold, it becomes a 30 Kelvin superconductor. And so this compound, if you would formally count the electrons, you would think you have a bismuth 4 plus and a half-filled bismuth compound. And if you actually, there's lots of literature out there about DFT calculation in like an averaged undistorted structure, and it has a half-filled band and looks very unstable. But if you look carefully at the structure, you see that they're actually small and large alternating bismuth oxygen octahedra. So this means we have 3+ and 5+ oxygen alternating. And so instead of having this filling, we get this filling in a charge density wave, and we again have a band gap and a trivial insulator. So this is actually also, if you think about non-isomorphic compounds, this is some kind of trap we can walk into, that a compound might appear to be half-filled, but if you actually carefully look, it's not. Okay. And there are more of those fake half-filled bands. One is what I showed you already before, is this interphase calcium silicide, where you would also count 5 electrons per silicon. If you know that 2 of them are an S electron, you would think you have 3 in the P electrons, which would be a half-filled band, half-filled P band. However, because of the bonds, this is not happening. And so this gives me to the example of strontium iridate, which is currently the compound, a very heavily studied compound, predicted to be a non-isomorphic direct line node material. And if you would count the electrons here, you would also figure out that it has a half-filled iridium D band in this electron count. And so there are so this strontium iridate actually forms 2 different crystal structures, this orthorhombic one here and the monoclinic one here. So if you just make a normal synthesis, you will always get the monoclinic one, and the monoclinic one has iridium bonds, so this will be gapped again. So it's the same kind of Zinto concept. This phase, however, does exist. It is a high pressure phase, and it has been done. The problem is that you cannot be 100% sure with high pressure phases that the structure is solved completely correct. Okay, the crystallinity is often not good. Not everything which is listed in the ICSD is correct. And so if you, maybe this exists and it has a half-filled band, but maybe there's some really subtle distortion people have missed so far. And so here's an experiment where they grew strontium iridate as a thin film in this orthorhombic form. And so here's the predicted DFT, where we have this nice non-isomorphic crossing at the U point. And then here is so the colored line are the measured RPIS, so here's the U point. And then the black line are the adjusted DFT, where they like added some, like played around with spin orbit coupling and some strain to model the sample. And you see here, there's a gap. So this crossing isn't completely there anymore. Also, there are lots of electron pockets and hole pockets trying to stabilize this. So something is fishy here. Like maybe the structure isn't completely correct, or maybe in the thin film it's a little bit different. I'm just saying to be really careful with what is listed there. Okay, so now I painted a really dark picture of non-isomorphic materials, and I still want to give you a way out. And so maybe there's a chemistry trick that can help us to find actually a non-isomorphic material which works and which is stable. So if you think about this half-filled band, this is basically like a single electron sitting off some side. And in chemistry, we call this a radical. So a molecule like this one, where there's one unpaired electron, is called a radical. You might know this from like the sun makes radicals in your skin, and that causes cancer, and then you use some vitamin A lotion because that catches the radicals to be okay. Okay, those are so radicals are really highly reactive compounds. So those ones I drew here, they're often used in polymerizations to make plastic and things. So you have one of these radicals, and because it's so reactive, it makes a chain reaction, and then you have plastic material. But there are some stability rules about this in chemistry. So by cadmium atoms with just H's, the radical is super unstable. If you put some organic residues to it, it becomes more stable. And then you can also put residues where the electron can be delocalized over those double pi bonds, and then it becomes even more stable. And then finally, you can make a radical like this, where this single electron can now hop around all those sites, and this compound is actually stable. This radical is stable at room temperature. I mean, it's not that stable, don't get me wrong. Like if it sees a little bit of oxygen, it's dead, but at least you can handle it for some time. Okay, can we transfer this knowledge to inorganic chemistry? Well, so also in inorganic chemistry, you can have something which is similar than a molecule, and this is called a cluster compound, where metals form bonds similar to energy, and they form this metal clusters here. So this, for example, is a very famous Chevrel phase, and this is a superconductor. It's famous for being superconducting compounds with lead, and you have this metal cluster. So you could maybe also delocalize this electron over this different amount of sites. And so, for example, this cluster also has an odd number of electrons per site where it's delocalized. However, this is a isomorphic compound, so this doesn't help us in this case. But if you look at the original paper of Chevrel, where he reported this Chevrel phases, he reports lots of different sizes of the cluster. So this was the one I just showed you, but they can extend along one direction. And you can also make an infinite cluster here. And then here you have a screw axis, and it actually crystallizes in a non-isomorphic space group with a screw. And if you look at the compound where this infinite cluster was there, it was actually not a charge balance compound. So it has 4.3 valent electrons per molybdenum, something odd. So then there was with Quinn also at Princeton, we looked at this compound. And so here again, you can see the screw. You have 3 molybdenums in this direction and in the other one. And then if you calculate the electronic structure of that, you will see that there are the non-isomorphic points relatively clean, relatively close to the Fermi level. Still not perfect, but maybe this is really an idea of delocalizing and this half-filled band over a large cluster amount of electrons to get this materials established. And this is the end of my first lecture. And then in the second one, I will give you some more examples of compounds that work.
Mm-hmm. So what would be the rules for to look for some topological superconductor?
Oh, well, yeah, so finding superconductors with chemical rules is actually not that easy. So it has been done for a long, long, long time, but it's not really a good recipe there. So there's just some trends. Whereas with the Dirac materials, we are much more specific, right? We are just, okay, we need those things, and then we can calculate the band structure, and we really see it. So with superconductivity, we kind of look for compounds which are close to an instability. So things with half-filled bands are also good, because when if they don't distort, they might become superconductors. But it's much more hand-wavy. So we can, of course, apply those rules, which has been found in decades for superconductivities, like looking for Van Hove singularities, half-filled bands, and try to find a topological superconductor this way. And maybe it appears by hunting the non-isomorphic ones, because you're already looking for half-filled bands. Yeah.
You were talking mainly about one-on-one phases, and then
Mm-hmm.
switched to the large clusters that you showed
Mm-hmm.
at the end. But non-isomorphic crystal groups are most common. So is there? What about other types of compounds? And
Yes.
How does that come into play?
Yes, you can also look for non-isomorphic 1-1-1 phases. However, then you will have the problem with the half-filled band a little bit. So actually, in my second lecture, I will talk about non-isomorphic 1-1-1 phases. And you will see that it will be really difficult to not have any pockets there to stabilize the non-isomorphic point at the Fermi level.
No, but my question was, what about things that are not 1-1-1 phases and not clusters?
Oh, well, the cluster idea is the idea to stabilize the half-filling, right? So if they're not 1-1-1 phases and not clusters, you will also, again, because they're not cluster, run into the problem that there will be pockets stabilizing your non-isomorphic point. And if it's very clean at the Fermi level, I bet you some kind of distortion happens to get rid of this. Yeah.